Hey everyone, thank you so much for joining this session. Let us know where are you joining from, and yeah, we'll be getting started in a couple of minutes. All right. Hey everyone, let us know where you're joining us from, and yeah, uh, what your experiences are with Hudi Presto, and yeah, we'll be starting in a couple of minutes. All right, just a couple more minutes to let people in. Please let us know where you're joining from, and yeah, uh, if you have any questions for us, we'll be happy to take them in the end of the show. All right, I see people joining in. Probably start in a minute or so. All right. I think we are good to get started. So, thank you everyone for joining this session. Today, we're going to talk about how we can use some of the important data management capabilities provided by Apache Hudi, such as metadata table, clustering service, and basically combine it with the power of a SQL-based query engine like Presto for your interactive analytical workloads. So let's quickly do a quick round of intro, and then we'll go from there. So my name is Dipankar. I currently work as a staff developer advocate here at OneHouse.ai, where I focus on open source projects such as Hudi and Xtable, and I have previously worked on other roles such as BI, data architecture, and machine learning. I'll let Ethan go first, and then probably Kirsten as well. Yeah.
Hi everyone, I'm Ethan. I'm currently a data infra engineer at OneHouse. I'm a Apache Hudi PMC member and driving the key initiatives in Hudi 1.0 release. Before joining OneHouse, I was at Uber driving some projects around networking and data.
All right. Thanks, Ethan. Kirsten here. Yeah.
Yeah, hi everyone. I'm Kirsten. I am an open source developer with the IBM Watson Open Technologies Group. So right now I'm contributing to Presto pretty much 100% of my time, but I have previously also contributed to PyTorch and a few different projects in the Jupyter ecosystem as well. Glad to be here.
Thank you so much, Kristen. All right. So, so in terms of the agenda, we will start with basically, high-level introduction into Hudi, how this all got started, right? And how things look at Uber from that point of time, and how it kind of enables lakehouse architecture. Then Ethan will cover about the metadata table and clustering table service, and how it is kind of important to optimally lay out data for query engines to be able to query data faster. And then we will have Kirsten from Presto side talk about the Hudi Presto integration and Presto in general as well. And finally, we'll end up with some of the results from some experiment, and we'll take some time for Q&A as well. So let's take a step back to understand how Hudi started, right? Because the problems that were seen at Uber back then, when Uber was in a hypergrowth mode, they were moving from a data warehouse to a data lake. And the problem was whether you have cloud object storage or on-premise Hadoop file system, it is an immutable storage system, right? So you basically had to put a database or a transaction layer on top of the data lake to work with. And that's basically how Hudi kind of originated. So the problem that Uber ran into specifically was with their kind of trips data set. And like everyone else at the time, they were kind of doing bulk uploads, right? So this entire process took them like 120 terabytes of data every 8 hours to like convert from one format to Parquet. And when you do that, they do a full recompute of all the downstream tables again. And basically the end-to-end data freshness would be around like 24 hours or so. So they noticed that their ingest performance was really bad, right? With a ton of unnecessary reading, writing, and I/O compute spend. Also, there was no guarantees that this job would kind of finish right successfully, because these were kind of massive tasks that might just fail. On top of that, there were no things like concurrency control, no atomicity guarantees, rollback, nothing of that sort. So this was kind of the basis of how Hudi started, right? And as you can imagine, these are much more complex problem to solve than just having purely table format, which basically focuses on things like metadata access. So Hudi actually started with the whole range of database problems, if you may, like things like updates and incremental processing, deletes, and on the data lake, right? So when Uber started to tackle these problems, they realized they weren't facing a completely new problem at all. Like pretty much all of the database system dealt with this kind of challenges, right? It is just that they needed a way to figure out to implement these that it kind of fits to the data lake kind of architecture, right? So essentially, what they decided was if they could build a system that could be, capable of handling updates, deletes and upserts, you can absorb these changes faster in the form of a table. And while you're able to do things like faster update, you should be able to consistently, like, query the snapshot, the latest state of the table, right? So no dirty data, and and see things are either committed atomically or not, right? So that's really good to have. Plus the ability to look back at specific point in time, and do queries like things like time traveling and those kind of thing. So if there is a mistake as well, you can basically track back to when things were right, and basically hit rewind from that point of time. Also, it wasn't just the ingestion problem. There was also the need to incrementalize the downstream ETLs, right? So for instance, can we consume only the changes that were required, right, instead of the full kind of recompute, which is really expensive as well. And that led them to build the incremental changes, right? So which is very core to Hudi, and also like separates it from the other open table formats out there. So all this principle, they basically guided the core primitives of Hudi, right? Things like upserts we talked about, you are absorbing the changes as they come, and are able to process the records faster, right? And there are things like incremental reads, like that is really core that we talked about, like you obtain the record that are only changed from that point of time, and you kind of use that for your processing downstream. And things like snapshot isolation as well, which is really like important for being able to have deal with things like multiple write and reads, and it's important that you have different services running on the background, so you need to be able to consistently query the snapshot data. So when Hudi started at that point, it was referred to as a transactional data lake. Today we have much like terms like lakehouse, like, but of course the idea was pretty much the same. So you start with your cloud object storage, where your data files, like for example Parquet, are sitting. Then you throw in a bit of metadata layer on top of that, and a transaction log on top of that. So basically, in a way, you are trying to like set it up as a like kind of transaction layer on top of what the cloud storage provided, right? So after that, you expose some of the APIs, right, which can be then utilized by the different compute engines like Spark, Flink. It can be utilized for reading and writing. And this was actually a pretty new and innovative way of doing things at scale, right, even at that point of time. So this was really like kind of like the core principles of setting the kind of lakehouse architecture foundation. Hudi also introduced two kind of storage type, or table types, copy on write and merge on read. We are going to talk a bit about them later today. which is also super important in how kind of Hudi deals with the changes in the records and stuff. So these ideas are right now kind of heavily borrowed outside of Hudi and adopted by other table formats as well. So we'll discuss a bit more on these table types in a few minutes. So once Hudi had all these kind of capabilities, the resulting kind of architecture was basically like a database abstraction, like I mentioned, right? But on top of the cloud object storage, or whether it's on-premise Hadoop file system as well, specifically by decoupling storage and compute. So now we can have things like faster upsert. Different type of indexing schemes were actually built in Hudi, right? Which is again very unique to other table formats. And you can incrementally build ingest table, which is also super important. So incremental processing, like I said, as a concept is actually pioneered from this. For instance, like instead of ingesting 120 terabytes of data every 8 hours, right? You could just now upsert a few gigabytes of data every 10 minutes in incremental fashion. So this really makes for efficient ETL downstream, and it's super efficient downstream wise. So Uber actually builds most of their core warehousing tables in kind of an incremental fashion, where they actually process only the incremental changes every few minutes. And then kind of run them. So this is not as ubiquitous as we could want it to be today, but we focus a lot on these aspects with Apache Hudi as well. So moving on, we have come a long way from those kind of beginnings, thanks to the diverse community contributions that kind of today serves Hudi serves as a foundation, right, for lakehouse architecture. So what is a lakehouse, right? As you I might have guessed from the name, and it's kind of really ubiquitous now as well. It's a combination of the data lake and the warehouse. But of course, this is not just a mere combination of the two, but the whole idea is basically to take the best of the both worlds. So for instance, data warehouses have, great data management and optimization capabilities, things like compaction, clustering, ability to kind of do things like time travel, schema evolution, upserts and deletes. And most importantly, with those kind of ACID guarantees, right? That's super important as well. So that kind of ability to do things in an environment like this would be super important. And on top of that, data lakes, right? From a data lake perspective, they provide great scalability, right? Specifically now with cloud object stores like S3 and Azure, all these major vendors. Cost-wise, also these object stores are very comparatively cheap, right? Which is really great for organizations to adopt. So a lakehouse basically builds on that idea, and one of the core ingredient or component in the lakehouse architecture is basically the table format, and Hudi enables an open table format. But it is also important to note that Hudi is much more than a generic kind of table format, because we talked a bit about the integration of kind of various table services and platform services that are designed for data maintenance and ingestion capabilities within the platform of Hudi, right? So all these things like data quality even, right, for that matter, right? So these kind of things Hudi actually makes a comprehensive data lakehouse platform. So in terms of the various components in general involved in a lakehouse, you can see it from the diagram here. We'll start from the bottom. On the bottom part, we have the kind of the lake storage where the data lands after ingestion from various operational and transactional system, right? These are kind of the major vendors that I talked about, whether it's a S3 object store, whether it's Minayo, like a S3 compatible API. Basically, they support storing any type of data and provide the required performance security, right? And then we have the file format on top of that, which is basically where the actual bytes are written, right? So usually, in columnar formats, provided advantages either you want to take advantage of things like compression or reading or sharing data across multiple systems. It really provides those advantages. And on top of these, you have the kind of Hudi's transactional database layer, and this is the layer where actually Hudi kind of shines, right? We talked about how it offers various table services, like indexes, concurrency control mechanisms, performance optimization capabilities, right? So these particular services, they collectively offer kind of significant enhancement to the data and table management, if you may. And then we see on the right hand side, there are a couple of metastore catalogs, that are basically exposing the data to other systems engines like Presto, and you can take it from there. Or also you have the downstream ML and BI tools that can be used to process the data from Hudi. So until now, we have kind of got an understanding of what a lakehouse architecture is, how we started with Uber at that point of time, how Hudi started, and basically how it kind of lays the foundation, right? So now let's delve into some of the specifics of Hudi, specifically the Hudi's table format, right? And it's important to understand how it kind of lays out the file in the file system, because there are certain advantages towards that as well. So two logical concepts that are important to take away from this slide. One is the file slice, and another is the file group. So a file size is basically, it contains a base columnar file, which is mostly Parquet produced after a certain commit or compaction time. And on top of that, it also contains kind of a log file, which is basically specific to only merge on read table. And I'm going to like talk a bit about it later. But basically, these log file contains the update to the base file since the file was kind of last changed or last produced, right? So when we have a group of such kind of file slices, we basically call them as a file group. Okay. And when a write comes in, for example, when the records are written, right, for the first time, the records are written to the file slices, right? And each record has kind of a key that is mapped to this particular file group. And this assignment of like the record key to that particular file group, it really never changes. And that gives us the advantages in terms of like, understanding what record to update, when we are doing things like updates and upserts, right? So really those kind of like faster, benefits are there with that kind of a design with Hudi. Some of the advantages, right, with this kind of a file layout, right? First, from the point of writing the data to the Hudi table. So if you have multiple table services, for example, like compaction, clustering, these are running in the background alongside your ingestion, right? These services, they won't block really each other, right? Because of like the multi-version concurrency controlling mechanism in Hudi, it really gives those advantages. So you can really have those things run, in parallel. And second, from the point of view of querying the Hudi table, right, from a query side, this particular layout allows you to like query data from a particular point in time and, be able to like query data from a particular like a snapshot. And on the bottom half, we see two important things here, just quickly to like, touch upon these things. One is the timeline and one is the metadata table. So timeline is really important to Hudi. It's basically essentially an event log, and it keeps a track of all that has happened within the table, right? So when a records get written to a particular file group, Hudi's timeline will record, what commit action was done in that particular timeline, okay? And it keeps a track of all those things. And then there is the metadata table, which is actually kind of an internal Hudi merge on read table. And, we'll cover a bit about this later. But at a high level, it stores things like, partition info, like file level statistics. Essentially, like we have built a multimodal indexing system in this particular area. So, you can basically take advantage of this metadata table to like reduce your extensive file listing, and better query planning and those kind of things. So now let's quickly touch upon the different kind of table types in Hudi. And it's if we try to understand the problem, right? Okay, we have a table, we have a bunch of per K file, right? And, let's say we make a few changes to the record, right? What are the different ways to deal with it, right? And how Hudi handles that thing, right? So copy on write and merge on read, deals it a bit differently. So file slices in a copy on write table only contains of the base columnar file. So we talked about in the last slide, right? We had the kind of base columnar file, we had the log file as well. So for the copy on write table, it's only the base columnar file, right? And every time you commit new data, Hudi makes a copy and produces a new version of this file. And you can see like, different color-coded version of the file, basically for different commit types, right? So let's say in the commit time 0, you insert certain records like A, B, C, D, E, and Hudi lays it out into 3 files, let's say, right? And, Hudi provides different query type to like query the data. For example, there is snapshot query, which basically allows you to basically query the latest snapshot of the data, right? And then there is incremental query, where you only see the new data that is written to a particular table after a given commit or compaction. So in this case, if you do a snapshot query, at the first commit time, you'll get all the records. Same for incremental one as well, because it's just one commit. But in the next one, when we update A to A prime and D to D prime, Hudi actually creates a copy of that, right? And, as you can see, the file 1 and the file 2 has changed because those records are present there. But the file 3 is untouched, right? Because there is no record in that. So now if you do a kind of a snapshot query at that particular point of time, you'll basically get the latest snapshot, which is like A prime, B, C, D prime, and E. But if you do an incremental query, you will only be able to get like the change data, which is really what we talked about in incremental processing. So one thing that you might have figured out that is copy and write has a much higher write amplification, whereas on the read side, the amplification is kind of 0. So this is kind of a much desired property, right, for a kind of read-heavy analytical workload. So that really demands from that. And the second table type is merge on read, which is basically actually, it's kind of like it's more operational things that needs to be done, but the core idea is the same, right? So everything is same until we do kind of like the first insert. But when we like change the record from A to A prime, here we don't rewrite the entire Parquet file, right? Unlike the copy on write. So usually for most of the scenarios, you could be just updating one column, right? Or row or whatever. In such cases, you don't need to rewrite the whole file over and over. So what basically Hudi does is Hudi basically stores this incoming updates into a log file. We talked about this log file a bit. And eventually, by applying a compaction process, Hudi will merge this base file with the log file and produce a new version. So when we do a snapshot query, at commit time 0, you're able to pull all the records, and same for incremental one at the commit time 0. But also for merge on read table, there are certain specific query type called read optimized query, which basically allows you to query, like choose the query performance over the freshness of data. So with a read optimized query, what happens is we will be getting just the record from the base Parquet file, right? Without the merge happening in the background. So, same for this particular thing. For commit time 1, if we change the snapshot query, we'll get the A prime, B, C, D prime, and E. Whereas for the incremental, we are getting the latest one, which only the change record, right? Which is A prime and D prime. And for the read optimized query, we are only getting the record that were present from the latest like Parquet file, like the latest base file, right? So that is pretty much it. Okay, so we have seen some of the key problems in a data lake and how kind of Hudi kind of solved that like in the beginning of the journey. And now at least like, we are at a point that where we are trying to deal with other problems as well. So the one important thing to note here is that just to be able to efficiently query large volume of data, it requires your storage layer to be optimized in a way that is favored by the query engine, right? So one problem in analytical workload is the difference in the arrival and the event time, right? So you always want to write data as it comes, but you might end up that way writing by arrival time. So for example, in this case, you see like that we're writing the data as it coming. So if you're having a query by city, the cities are really scattered over all the files. So for the queries to be really benefited, you might want this particular cities to sit together in a single file, right? And there are also things like expensive file listing, the S3 or any kind of like storage system. They are kind of throttle with kind of large request limit. And there are problems with small file as well because we are writing data as it arrives, right? So we are writing more smaller batches of data. So that is pretty much it from the problem side. Now I will hand over to Ethan, who will basically cover and talk a bit about how we can address these problems. So back to Ethan.
Thanks, Debunker. So next, let's talk about the key component in Hudi, the multimodal indexing. Nadine, if you can bring up the slides, that'd be great. Thanks. So as the name suggests, like multimodal indexing, Hudi is the kind of the key part for the data lake. So as you can see from the name index, for traditional database, they always have an index for locating records and information needed. So similarly in Hudi, we also store like index and metadata for helping listing files, query planning, and applying any kind of optimizations for both read and write side. And this type of metadata or index metadata can be pretty large. It can be small as like a few megabytes, or it can be as large as like a few gigabytes, even terabytes. For example, if you want to store the record level index. So that's how we designed this multimodal index in Hudi. So we have this generalized indexing subsystem so that can scale to 10, even to 100x of data on the lake. So this, we call it metadata table. So the metadata table can store like even terabytes of data. And it improves both the read and queries beside writes to the table. Alongside that, we also designed this indexing to be asynchronous, so that alongside with ingestion, async indexer can build indexes concurrently without affecting the latency of the real-time ingestion. So the key principles behind designing this multimodal index is we want to actually scale metadata, as already mentioned. So we use the internal MOR table type for this metadata table. And to make sure the metadata provided by this metadata table is consistent with the data table, we use ACID updates with multi-table transaction, meaning that the transaction is tied together between the data and metadata table so that metadata is always consistent from the internal metadata table. And we also have a mechanism to do fast pointed lookup. This will allow us to quickly look through like terabytes or even petabytes of metadata if we just want to look for example, the column sets for one column, like the min and max. So next, let's show some performance improvement for one particular index metadata, the list of files. So as Debunker already mentioned, listing files on cloud storage is very expensive because cloud usually enforce the throttling so that listing a large table, for example, thousands of partitions, that can be very slow. can take up to like tens of seconds or even like few minutes. So in Hudi, by default, we enable this files partition to store all of the list of files for all the partitions. So on this slide, we show like the benchmark listing hundreds of thousands of files across thousands of partitions. So if we directly list that using Cloud Storage API, then it hits throttling because for each partition, it has to do its individual listing, and then to return result, it has to go through several API calls. And it's bottleneck on actually the listing for the reads or writes. If we use the Hudi's metadata table to do the same job to get the file list, it can provide actually 2 to 20x speed up because these metadata are well organized in the internal metadata table, like the multimodal index, and they are stored in like just like a handful of files. So reading those to provide the listing is really fast. So these not only applies to the file listing, it also applies to other types of metadata we have in Hudi, like column stats, including min and max, like the Bloom filter metadata, and also the record level index we introduced in recent 0.14 release. So multimodal index provides the foundation for actually of the information we needed for optimization. So next, let's talk about how we can actually use that, and then also use the table layout to optimize the query performance. So particularly, we are interested in the clustering table service in this talk. So what can clustering help? So as Dipankar mentioned, one problem we have is for faster streaming ingestion, usually the batch size is pretty small or even tiny. So there's not enough data to write larger files. So usually file sizes are pretty small. And small files are not good for query engines to do the scanning fast. So that's where clustering can help here. So it can automatically size the files alongside the ingestion. So there's no compromise on ingestion, but on the background, it kind of bundles all the small files in a larger file. And Hudi manages so that for the latest snapshot, after clustering, it reads the larger files instead of the small ones. So here I show example, let's say for streaming ingestion rather, each batch writes 10 MB files in each partition. So there are multiple batches. After that, if we trigger clustering, we can basically rewrite all these files into a larger one, like 100 MB files. So that there are fewer files and files are larger, it's better for query engine. And in Hudi, we allow users to plug in any kind of clustering strategy, meaning that what files to cluster, how you cluster it can always be customized. So let's say later on this job gets more data per patch and it writes like 50 MB files. So if we already say we want 100 MB files, we don't have to recluster previous files. We can just cluster the latest files, like the 50 MB files, to another 100 MB files. And then after that, let's say I want even bigger files in the table. Then you can change the clustering configs and strategy so that it groups the latest written files with the previous data, like previous files with the old data, into an even larger file. So this can all be customized. So we talk about how clustering solves the small file problem. So the third problem we are tackling is like the query latency. So one key to optimize query latency is actually reading fewer bytes from input tables. And there are three aspects here. So as I already mentioned, indexes are helpful to locate potential records in the table that needs to be actually fetched. So it will be helpful for these kind of needles in the haystack queries. These will help actually identify the data. This is one way. The second way is caching. So let's say if I still want to scan the data from the storage and I need to read the files, but you can build a cache in the middle, let's say some disk cache or even memory cache. so that you don't have to reach out to cloud or reach out to other places. You can just read from the cache so that you can reduce latency. So the third way, which is of particular interest in this talk, is the storage layout. So what does it mean? So it controls how data is physically organized on storage, meaning that what records are in which files. So we'll see how this can actually affect query latency in the next few slides. And clustering is particularly solving this problem, so to reorganize the data on storage so that it's better for query engine. So you may wonder why we need clustering. Like, is data already organized when it's ingested? So if we look at the problem, or if we look at the query versus the ingestion ordering, so usually ingestion order is based on time, for example, trips by time. But when we do the analytics, or we may do want to process the data in the subsequent pipeline, we may not just use time, or we are interested in other dimensions. Like, for example, I want to group the trips by city so that I can see the counts, the average trip size, etc. So the data locality for query is drastically different from the ingestion order. So that's where we need to reorganize the data, and how clustering in Hudi can help. So besides auto file sizing, it also recognizes data based on the locality actually query requires. And again, like, this can run in the background with no compromise on ingestion. So let's take an example of how that organization works. So with before clustering, let's say like the records in green are scattered all over the places in different files. So for query engines to actually read such data, it has to scan all the files. So that's going to incur a lot of I/O, and that's not efficient. So if we can somehow know, okay, I know like the data I'm looking for, it does not have a lot of data, like just like a few records. And if, by clustering, you can just sort by this particular column. Then after clustering, you see that all of these green records are grouped in just like a couple of files. So for engines, after planning, I just need to read these two files to avoid unnecessary errors. So here is a more concrete example of how clustering, after clustering with the optimized layout, query latency can be reduced. So you can see here, pipeline doing inserts to like a table, and then it writes a lot of small files, for example. Then the query wants to understand like the particular records from a particular session. So let's say this session is pretty long, it scatters like a few hours. So if ingestion happens every few minutes, then the records for this particular session ID is going to scatter across all of the files, or most of the files. So before clustering, then query engines has to go through all of these files, push down this session ID equals 123 filter or predicate, and then read all files, and then filter out the results for this particular section. So if we do clustering, after that, we cluster by session ID. First thing is, as I already mentioned, it basically merges small files to bigger ones. So we have fewer files. Basically, previously we have 10,000 files. Now we have 1,000 files clustered. And then along with file sizing, we also sort the data based on session ID. So that, this session, so assuming that this session has like only a few records, so it should only appear in one file. So after that, after query planning, I know I only need to read this one file. Then during the execution phase, only this one file is read. So this is how clustering helps to reduce the I/O and then ultimately the query latency. So as I talk about the benefit of clustering, let's talk about how Hudi handles or manages the clustering service. So clustering service in Hudi is self-managed. So it has two phases. One is scheduling. So scheduling is responsible for identifying the target data or files to actually cluster. And it generates a plan timeline so that it can be later executed. So during the execution phase, it takes the plan already generated on the timeline, with the pluggable strategy, as I mentioned, this strategy can decide how you execute it. And for example, you can reorganize data with different types of sorting, like can be linear sorting, or if it's multi-dimensional data, like location data, you can use Z-order curves and Hilbert curves. These are all supported in Hudi. And after clustering is done, replace commit is put into the timeline so that current engines know clustering happens, larger files and sorted reorganized data are done, then engines can pick up the latest files written by clustering. So there are different modes of clustering users can choose. The simplest one is inline, meaning that clustering happens sequentially after each ingestion batch if the latency or ingestion latency is not of big concern, or for batch jobs. And the main use case are like the async clustering, where the clustering happens asynchronously in the background alongside ingestion, so that ingestion latency is not affected while clustering is doing the same thing. So these, since clustering uses the MVCC, the multi-version concurrency control, so it does not cause conflict. So async clustering is supporting like 3 different modes, like using like Hudi streamer, Hudi structured streaming, and Flink streamer using like swap pool management. And you can also run in a standalone job asynchronously, like Hudi clustering job and Flink clustering job. And if user want to manually do clustering for like a particular clustering operation, they can use Hudi CLI Spark procedure. So that wraps up how clustering works in Hudi. And next, I'll hand off to Kirsten to talk about the amazing Presto engine and how Presto integrates Hudi to provide all these benefits.
Excellent, thank you. Let me try to share the right screen here. Okay, there we go. Okay, yeah, so, like Dipankar and Ethan mentioned, Presto is just one of the many integrations that you can use with Hudi, but I will take you through the why and the what of Presto in the next few minutes. So just a high-level overview of Presto. It is an open source SQL query engine. So Presto is ANSI SQL compliant, which of course means it's easy to pick up for those that are already familiar with SQL. And it is a Linux Foundation project, specifically couched under the Presto Foundation. So it has a really diverse community, diverse governance, and wide adoption. So Presto has 2 key things that make it a great part of a lakehouse setup. The first is that Presto was designed to be very fast. And this is of course important considering the huge amount of data that you're typically working with nowadays in a data lake or lakehouse. So Presto was originally developed at Facebook, where it was used to run interactive queries on petabyte scale data. And in fact, it still is used at Meta today for the same and even larger scale data. So basically, from the jump, it was designed with performance in mind. And we'll get into a little bit more specifics about why Presto is so fast in the next few slides. But the second key feature is that Presto has a really extensible architecture. So Presto can connect to various underlying data sources and also several high-level reporting and BI tools if that's what you're interested in. So specifically, it's Presto's concept of connectors that make it possible to run SQL queries on basically any data source that has a connector implementation in Presto. And Presto also supports federated querying. So, depending on which connectors are available in your Presto instance, you can use one SQL statement to query many disparate data sources. All right, so let's move on. We'll take a look at a high-level overview of the Presto architecture. So the top layer here is that visualization BI layer. And of course, this is an optional layer. The center there is, I should also mention, there are other ways that you can connect to the Presto cluster, which is sitting in the center here. You can use Presto as a CLI, it has a UI, and several other various programmatic data access ways that you can make queries of your cluster. So the cluster here in the center is a very small one. Of course, we have just a single coordinator and 3 workers, but you can just as easily scale that up a ton and have a Presto cluster with hundreds or thousands of nodes, including a setup with multiple coordinators if that's what you require. Now, the lower layer is the possible connections to the underlying data. So you can have, connectors directly to a number of databases like MySQL, MongoDB, PostgreSQL, all those good ones. And that's sort of shown on the bottom right there of that diagram. But more importantly, for our purposes here, there are also connectors for table formats in Presto as well, of course, Hudi being one of them. And that's sort of what we see on the bottom left here. So connectors for table formats like Hudi handle accessing the underlying storage for you. So, of course, in a lakehouse setup, that's going to be object storage or HDFS potentially. But the connectors for these table formats also provide some extra functionality specific to that table format, for example, ways to view the various metadata layers that are handled by that table format. All right, so as we mentioned previously, Presto is fast, but what makes it so fast? This is just a glimpse. There are actually more reasons, but I don't want to bore you, so we'll focus on these ones. As we alluded to, in the Presto architecture diagram, so Presto is built on a distributed architecture, based on the massively parallel processing model. And this makes it possible to run, hundreds of concurrent queries on up to thousands of worker nodes. So as you can sort of see in this diagram on that bottom right, workers basically work on all their tasks in parallel, and each uses the relevant connector to access whatever the underlying data source is. So, using the example of a federated query, that connector and data source will potentially be different. Presto also does as much processing as possible in memory. So, workers are going to execute their tasks in memory, but also this includes the in-memory streaming shuffle that exchanges intermediate data between nodes, at the end of query stages. So any opportunity to, reduce disk I/O latency is taken in Presto, especially between query stages when there can potentially be a lot of lag. So speaking of query stages, Presto also has an efficient stage and task management process. Again, if we take a look at the diagram, you can sort of see how Presto breaks down a query for analysis. So this portion happens in a coordinator node, and first an ANTLR parser converts the SQL string to an abstract syntax tree. It's then validated, and then finally it's converted into a logical relational tree. And that's sort of what's loosely represented here in the dark and light blue, which are the stages and the tasks that Presto has, determined as what's going to be the most efficient way to perform and get the results for this query. Now, part of this logical tree also includes several built-in query optimizations that Presto does. So this might include some rule-based optimizations like predicate pushdown, might have some cost-based optimizations like join reordering, anything that it can do to make the query as efficient as possible. And if you're curious for more info about this, can be sort of a complicated topic, how Presto breaks the query down into stages, definitely check out, run a Presto query and check out the UI. The live query plan feature is really good at breaking down into detail what those stages and tasks are and which workers they're assigned to, and it's a really helpful feature. All right, so Presto is fast, that's great. But the other big piece, as we mentioned, is the concept of Presto connectors. So Presto can basically connect to any data source that has an implementation of the Presto API. including, proprietary sources as well. So it's this implementation that ultimately determines, what functionality of that native source is available for Presto to take advantage of. And it's quite easy to set up a connection from Presto to a data source, or as they're called in Presto, a catalog. You really just have to add a configuration file into the directory that Presto expects to find those configuration files, and you're good to go. So this configuration file is a .properties extension, and essentially it includes all the information that a Presto node would need in order to access the underlying data. And it probably also will include some other options that tells the Presto nodes, specific configuration or preferences regarding how you want the data to be accessed or viewed. And the Hudi connection works, exactly the same way. Even though Hudi isn't providing the data itself, it is still going to act as the proxy in order to get to that underlying data source. So you really only need the single properties file. And we have a simple example here where we're basically, as you can tell, giving Presto all the information it needs in order to access Hudi and its features and the underlying data. So a little bit more info on that Presto Hudi integration and what needs to happen in order to make that work. So it's again fairly simple. Presto needs 3 basic things in order to integrate with Hudi. The first is access to a Hive metastore. And then you're also going to want to provide network access from the Presto coordinator to the Hive metastore. And it's with these first 2 pieces that Presto is able to read the Hudi metadata that has been synced to the Hive metastore. And then finally, we also need, network access from all Presto nodes to that underlying object storage. So we saw all of these pieces in that simple properties file on the previous slide, but the Hudi connector for Presto, of course, supports much more in the way of configuration options than what we showed. The Hudi connector actually supports all of the same metastore configuration properties that the Presto Hive connector does, which is quite a few. So once you have all those pieces in place, you can make the following queries types on the relevant tables from Presto. So with copy on write tables, you can do snapshot queries. And with merge on read tables, you can do both snapshot queries and read optimized queries from Presto. And this is, of course, just the status quo. There's plan to support more functionality in the Presto Hudi connector in the future. So if this is something you find intriguing, Presto would certainly be extremely happy to accept enhancements or documentation improvements or any improvement from the community at large. So please feel free to join our Presto Slack, and we can answer your questions there and talk a little more about the Presto Hudi integration. So now I'll throw it back to Dipankar, who will take us through some of the real life query stats for the Presto and Hudi integration.
All right. Thanks, Kirsten. Yeah. All right. So some numbers. So just to quickly share some of the benchmarking number that we kind of ran, and to give an idea of how basically Hudi's kind of clustering service accelerates the query performance. So let me start. Okay, so we used the GitHub archive dataset for this benchmark. It spanned like 6 months of data. Total data was roughly around 220 gigs with 450 million records. We used 3 different flavors for comparison. The blue bar, it represents the out-of-the-box scenario. There is no optimization involved. The red bar is basically sorting, and the sorting was based on 3 fields: the repo ID, the type, and the hour of the day. And the yellow bar represents like zero-red clustering for the same 3 columns. So the first query involved the predicate on the repo ID. The second one involved the predicate on the type. And if you see in the top figure, it represents the read latency for both the queries in all the 3 flavors. So as you can see, with linear sorting, we could reduce the query latency by like, let's say 60 to 70% compared to a no layout optimization, right? Whereas with Z ordering, you could even see more gains, depending on how the layout was, how the query was. but it's 70 to 80% reduction in query latency. On the bottom one, you can see the amount of data read, like just to highlight the amount of data scanned from a particular engine side. So with column stats index over optimized storage layout, we could reduce the amount of data read by 75 to like 90%, to extreme cases. So basically, the takeaway was that the linear sorting, it suits best for like hierarchical data, whereas Z ordering, it really works good for like co-locality and kind of multidimensional like clustering things. So all these are not possible without a diverse community. And over these years, Hudi community has grown significantly. Definitely a shout out to like the community that has grown to like 19 PMCs, 36 committers from like diverse background, and that diversity is super important as well. Our GitHub engagement is well above 6,000 users, and just in the last 2 years, we were like answering like close to 4,700 questions in a Slack channel, which is a really good place to be able to like talk about things of how things are done in production, the issues that it might be facing, and those kind of things. And of course, the Slack channel is like the community is really increasing, and there's a huge momentum out there as well. So some resources for here for you to join the community Slack. Like we said, like a lot of engaging discussions. There are also like our social channels where we kind of post regularly about all these updates that are happening in the world of Hudi, and all the different kind of like side from the compute side as well, like things like Presto and how it works and how it nots. So really good place to just sign up for those kind of things as well. And if you're interested to like check out our repo and code, like, and are ready to contribute as well, feel free to do that. So with that, I want to do a quick call to action. So we will be touching upon all these aspects of Hudi that we talked about with Presto, specifically things like creating Hudi tables, like inserting data, things like upserts, all those kind of clustering and metadata table. We'll be doing all those things in a workshop setting, which is happening on April 24th, and that will be more of a technical kind of hands-on session. And I think it'd be a great learning experience for like to learn about how to build open lake houses using Hudi and Presto on S3. We'll take the TP series data set, like a good sizable data set, and run all these things that we talked about in the infra that is provided by us. So that is all that we had today, and I think we can take some question answers if you might have. Thank you. And obviously, like for the workshop, we'll be happy to share the registration details probably by next week or so. All right, let's see if we have any questions. I don't see anything that is up now. I think a few have been answered on the chat, and there might be some delays on the chat. So if you're putting in your questions there, we should be able to like get back asynchronously as well after the session as well. So I think that is all. Thank you so much, Ethan and Kirsten, for joining me in the session and just talking about the benefits of what Hudi and Presto has to offer. And hopefully we'll have more time on the workshop, and we'll take it from there. So thank you so much.
Thank you.
Thank you.
All right.